I want to talk to you next about electric fields. We're going to talk actually very briefly about electric fields. Hopefully you learned some from the MIT videos. But remember that the electric field, every charged particle modifies the space around it and produces what we call a field. An electric field is a place where if I brought a charged particle into that field, it would feel a force. But a force is an interaction between charged particles. And I don't know that the electric field exists really until I bring another charge into it and I see what happens. So an electric field, if we have a charged particle, maybe we have a positive charge here, all the way around the charged particle exists an electric field, and we model that electric field by using electric field lines. And electric field lines point away from positive charges, as you saw yesterday, or hopefully some point in the MIT video, and they point towards negative charges. So all around a charge is there an electric field. Now, I don't really know that the electric field exists really until I bring something into that space. And then that object I bring into that space is going to feel a force. So the electric field is a useful concept, and we define it, the electric field, as the force a charge would feel if I brought it into that space around it, Q being a little test charge. So if we think about what that means from Coulomb's law, right, if the force on a charged particle is KQQ over R squared, and then I divide that by Q, then I end up with the fact that the electric field is KQ over R squared. Now, the beauty of the electric field is that if I know the magnitude of the electric field at any point around a charge, then I can determine what the force on a particle is going to be when I bring it to some distance, r, right? All I got to do then to find out what the force on it is I just take the magnitude of the electric field generated by this source charge, and I multiply it by a charge that I bring into the space around it. Now, if we go back to what we did when we were calculating forces, our 3-point charges here, Q1, Q2, and Q3, right? And this was our answer for this problem. The force, the net force on Q3 here was 2k q squared x over x squared plus d squared to the 3/2. Now, if I want to know about the electric field here, and let me change my pen color, make that purple. And then let's go back to the screen here. If I want to know instead what the electric field is, right, electric field would be the force, the net force, or the net electric field, net force over Q. Now, where do I want to know the electric field at? Well, let's say I want to know what is the electric field. What if I take this charge out? Right here. And now I only have these two charges here. I want to know what is the electric field here at this point due to those two charges. All right, well, what did I do? I just took that Q away. Right, that Q is not there anymore. So what I'm going to do then is, since this is the force, this equation right here is the force on that charge by these two charges, in order to find the electric field created by these two charges at this point, all I got to do is take this, my 2kq squared x over x squared plus d squared to the 3/2, and I just have to divide that by q. All right, so what happens then is I get rid of that q. And the electric field here at this distance, which is square root of x squared plus d squared here, the electric field due to these two charges at this point is 2kqx over the quantity x squared plus d squared to the 3/2. So I took out that q, and I want to know what is the electric field at that point. And of course, we could do that again on this slide if I wanted to know, if I want to take this charge out right here, and I want to know what is the electric field here. This is purple anymore. If I want to know what is the electric field at this point, now due to these three charges? Well, all I got to do is get rid of one of my Q's here. All right, I took away that Q. So the electric field, then if I want to know what the force is, well, just stick a Q in there, and I multiply each of these numerators by Q. So the electric field is a useful concept. It gets more complicated, however, when we start having things like lines of charge, or arcs of charge, or disks, charged disks. Right? Not everything is just a point charge. Life is not a point charge. Right? We have a conducting wire, right, with electrons flowing through it. We generate an electric field due to the motion of these charged particles, the presence of these charged particles. So what we're going to do when we come back to school is look in more depth at how do we figure out what the electric field is if instead of 3 charges, I have an infinite number of charges. Then how do I figure out what is the magnitude of electric field some distance from that wire? What I want to talk in more detail about is acceleration of charges in a uniform electric field. Let's say I have 2 parallel plates. And 2 parallel plates that I take a battery, maybe I hook it up to these, and I place negative charge on one plate, and that creates an equal but opposite charge on the other plate. So we would call these parallel plate capacitors. And in fact, we're going to do a whole other unit by itself once we get through electrostatics on parallel plate capacitors. Now, if you remember back to last year when we talked about parallel plate capacitors, we said that the electric field in between the parallel plate, right, it goes from positive to negative, there's my electric field, is constant. So in a parallel plate, I produce a uniform electric field. A uniform electric field, so it doesn't matter, let's say the separation between my plates is some distance d, it doesn't matter where I am with regard to the plate if I have a uniform electric field, that no matter where I put the particle is going to feel the same force, right? The force on a particle is the electric field times the magnitude of the charge that I put in that field. So if I have a constant force, that means I have constant acceleration. So if, let's say, I put a positive charge in this parallel plate, what's going to happen to it, right? It's in an electric field, it feels a force. I put this charge here, magnitude Q, it feels a force, right? And the force that it feels is in that direction. So the force on my particle, we said, was E times Q. And if I want to know about the acceleration of my particle, right, the acceleration when there's a net force, right, that's equal to mass times acceleration. So the acceleration on my particle, therefore, is the magnitude of the electric field times the magnitude of the charge that I put into the field divided by the mass of the particle. So Q and M, those have to do with the actual particle that I put in the field, whereas E has to do with the source of the charges that is creating this electric field. Now that I know how to calculate the acceleration, right, we could find out things about speed. What if I want to know how fast is this particle going when it hits this plate? What is the speed here at distance d? Well, now if we have constant acceleration, I can just do regular old kinematics, right? And if I want to know what its speed is at distance d, right, what kinematic equation would I use? Well, that would be what I call my indifferent equation, right? V at d squared is equal to v initial squared plus 2a delta d, right, our change of distance. We're going to say that my initial speed here is 0, right? That makes life easier. So that means that the speed when it hits d is the square root of 2 times the acceleration, right, which is eq over m, multiplied by the distance it travels, which is d. Now that I know the final speed, right, we could calculate how long does it take? Or I guess I could have done that, right, without knowing how fast it was going. We could use my least favorite equation, right? That would be x final is equal to x initial plus vi delta t plus 1/2 a t squared, right, delta t squared. Of course, the distance is d. Initial velocity is 0, so 1/2 the acceleration, which is eq over m t squared, and of course I could rearrange that and solve for t. Now that's if I put a particle in like this and it travels horizontally. Now of course if I have a positive charge here, it's going to accelerate in the direction of the electric field, right? So positive charges accelerate in the direction of the electric field. Right, because by convention we draw electric field lines from positive to negative. Obviously that's not the case for a negative charge. Right, if I go and I put a negative charge in here, right, if I put a negative charge here, is it going anywhere? No, it's at a happy spot. Right, so if I start it here, it's not going anywhere. If I instead start my negative charge over here, right, it's going to feel a net force in the opposite direction of that electric field. Right, it's going to want to go towards the positive plate. It's being repelled by the negative charges and attracted towards the positive charges. But again, the acceleration is eq over m. So positive charges accelerate in the direction of the negative of the electric field. Negative charges accelerate in the opposite direction. Of the electric field. And that should make sense to you. If electric field lines are drawn away from positive and towards negative, then the behavior of positive charges is going to be opposite of the behavior of negative charges. Acceleration, however, though, is going to be the same calculation, the magnitude of the electric field times the charge on the particle divided by the mass of the particle. What if, instead of putting a charged particle in here, right, that would be kind of difficult, putting a charged particle here and putting an electric field on and watching it move. However, something that we can observe is if we set up our electric field again, from positive to negative, so there's the direction of my electric field. And if I take a charged particle, for example, take a positive charge, maybe it's an alpha particle, and we give it some initial velocity that's all horizontal, we send it in here, what's going to happen? What's going to happen is it's going to behave like a projectile that was launched horizontally off like a cliff. Right? What's going to happen is this particle is going to come in here and it's going to feel that electric field, and it's going to feel a force then. I put a charged particle in an electric field, I'm going to feel a force, and it's going to be propelled downward. And a nice parabola, why? Because the force is only vertical. Like how I drew this, the force is only vertical. Right? So it's just like gravity, the acceleration due to gravity pulling it down, the force of gravity. Now, depending upon how fast I go, I could follow this route. We'll call this route for our this VI. But I could give it more speed, right? I could maybe make this, actually let's just put it in red. And what if I don't know, make it 5 times VI, what's going to happen? Well, now this particle for 5 times VI, I guess I should just leave it in blue, right, it would follow a parabolic path till it gets to here. Now, once it gets outside that electric field, oops, that's a lovely parabola, isn't it? Once I get outside that electric field, there's no more force on the particle. Provided there's no other charges in the space, there's no more electric field. So out here in the absence of electric field, it's not going to feel a force, and therefore, by Newton's laws, in the absence of a net force, a particle will continue in its state of motion. And so once it leaves the electric field, this will be the path of my particle with no E field present. In here, right, the electric field forces it down, and once it gets outside, no more force, so it travels in a straight line. Now, again, I only have acceleration in this direction, right? My force on my particle for a charged particle is going to be straight down, right? An electron would actually follow a different path, right? It would move up. Its mass is less, so acceleration value would be different if it was an electron, and its path would be in the opposite direction. In fact, you can tell what charge, which plates are which sign if you know the sign of the charge that you're shooting through the electric field. Its path will be very different. Now, in this case, right, the acceleration of this particle in the x direction is 0, provided there is no air resistance. If there's a vacuum here in the plates, then the acceleration in the x direction is 0. The acceleration is all in the y direction, and again, the magnitude of that is going to be the electric field times the charge of the particle divided by the mass of the particle. So in the x direction, right, if I want to know the speed when it reaches here outside, if I want to know what is this speed, the final speed at this point, right, because then that's going to be a constant speed once it leaves that electric field. How do I figure that out? Well, here, right, if we make a coordinate system, right, if this is my V final, that means I have a velocity, if I draw a little triangle here, let's make this in red, right, I have a velocity in the x direction, oops, not a very good triangle, and a velocity in the y direction. In order to find my net V final, right, that is the vector sum of these two components. Now, the velocity in the x is just going to be my initial velocity, right? I shot it in horizontally. The acceleration in the x is the same. And remember that when there's no acceleration, the only equation I have, velocity in the x, is the change in x over change in time. In this case, there's no acceleration, so V initial x is equal to V final x. Right, by definition, if there's no acceleration, there's no change in speed. So that means that if I blow up this little triangle here, right, there is V final x, there is V final y, and there's my V final net. V final x is just V initial x, I know what that is. My V final y, let's see. I would have to know something about the distance, wouldn't I? Or time. Let's say that the separation between these plates, again, is d. All right, so from a kinematic standpoint, V final y, we use, again, my indifferent equation, V final y squared is equal to V initial y squared plus 2a delta x. Initial velocity in the y, if this comes in horizontally, right, the initial velocity in the y is 0. The acceleration is our eq over m. In this case, the x is actually d over 2. And of course, that's equal to v final y squared. My 2's are going to cancel. So my v final in the y direction is going to be the square root of eqd over m. So I can plug that in here. And then, of course, my v net final would be the vector sum of those, or Pythagorean theorem. So v1x squared plus EQD over M and square root of that quantity. So just kinematics when we have uniform acceleration. If we don't have uniform acceleration, well, then our kinematics, we can't just use straight kinematics. We need to know something about the equation for the acceleration, and we can do some calculus.